then just like I had it last time, just ask questions, and they can cut you off, right, in a respectful way, like if
Oh,
they have a question.
absolutely, yeah. If anything, if at any point you want me to slow down or you have a question or anything, yeah, just let me know. I'm happy to be interrupted.
Yep, yep. And everyone knows how to use the raising hand function, right?
Yeah.
Yeah, so just use the raising hand function to notify him without interrupting him, or you can just text to the chat. This is going to be a really, really dope one. The last thing I've learned about black holes is that there's some connection to time travel.
I covered that. So you guys were really interested last week in black holes, so I figured it's a good way to kind of introduce a few important parts of astronomy, and it's a subject you would be interested in listening to. So yeah, I can just get started on that.
Go ahead.
To set up for anyone who wasn't here, I'm a student at U of M, about to graduate with a bachelor's in astronomy. I'm working with the Student Astronomical Society as well as the Society of Physics students to come and kind of give some presentations, and I'll probably be handing the torch off fairly soon here to someone else in the organization. But yeah, so black holes. I want to talk about it too because it's something I worked kind of personally with my first research project. I was actually researching a black hole candidate. But forward. So when I think of black holes immediately, this is one of the things that comes to mind. It might be kind of nerdy and specific, but a few years ago, just over a year ago, I think, this astrophysics team came out with this image on the right, which is the first image ever taken of an extragalactic black hole. Or sorry, not an extragalactic black hole, an extrasolar black hole. So what's on the left is a simulation, kind of a prediction of what they thought it would look like at a far higher resolution than we can actually make images. And on the right is the actual image they took. So that is the event horizon of a black hole, and it's the first time we've ever been able to observe them. And I'll explain a few reasons why that is. So the first thing to understanding black holes is kind of understanding how stars are formed. So every star will start out part of a nebula, which is just what we call kind of these big clouds of gas that tend to be somewhat more dense than other parts of the universe. And this chart is kind of misleading because there's kind of three options to start. You either become a massive star, an average star, or a less than average star. The life cycle of stars that are below what we would call average isn't terribly exciting because they never actually produce the conditions to start nuclear fusion, which is kind of the driving force of stars. And so if your mass is too small, you become what's called a brown dwarf, and you kind of just slowly get dimmer and smaller until you're just kind of an unseeable remnant floating through space. So next up would be if you're an average star. That'd be something kind of like our sun. These stars travel along something called the main sequence, and it's basically just this path that we see almost all stars travel along. Our sun is pretty much halfway through its main sequence life at the moment. And so as the star ages, it kind of starts to bear off that main sequence, and that happens because that nuclear fusion I talked about uses up material. So you turn hydrogen into helium when you fuse hydrogen. And so as the star works, it takes more and more energy to kind of force these particles to come together. And in the end, after they form, they actually end up releasing energy. But as more energy is needed, the star kind of collapses more and more. But at some point, the outer layers and the core kind of become separate, and the core starts to puff the outer layers up, and that's when we form what's called a red giant. And so those stars tend to be fairly cool, but very, very big, and so they're very bright. And one that you might know of, which kind of possibly falls between red giant and red supergiant, is Betelgeuse. It's in the constellation Orion. You can kind of see that it's redder than other stars, but that's only have very dark skies. What happens next is that process of puffing up just kind of continues until the outside of the star is no longer really star, and it's kind of just gas around what is now a fairly dense core, and that core will actually be what you see to the right there, a white dwarf. So this dense core produces what's called stellar wind, which is just basically, it produces a lot of light and that light kind of just pushes the material away. After it's pushed all of its material away, it then is a white dwarf, and white dwarfs are kind of weird objects, and I have a better explanation of what's going on inside them later, but for now, they're basically just balls of electrons being forced together, which is not a great way to explain it, but that's essentially what's going on. And so what's happening is they're really, really hot and very, very bright because electron degeneracy pressure, which I will explain later, is the only thing that's keeping them from collapsing into nothing. So now on the other track, if we have very massive stars, they do basically the same thing as average stars up until red supergiant. They kind of do that same fusing. They fuse hydrogen to helium. Helium then enters what's called the carbon, nitrogen, oxygen cycle, which is just how those kind of are produced. But at the end of the day, you have that same puffing that goes on where you have kind of multiple layers of different elements built up and they just push each other outward. Except in the case of extremely massive stars, instead of just dissociating completely, the center core fuses all the way to iron. And iron is special because it's kind of this tipping point where fusion takes more energy to start than it gives back to you. And everything below iron, you get more energy out of fusion than you put in. But everything above iron, it takes more energy. And so when that happens, the core of the star stops fusing entirely, it stops producing energy, and the outer layers of the star collapse in with it. And so now you have another split, and that is depending on, again, the mass. So the highest mass ones will directly form black holes. They collapse fast enough and hard enough that nothing can really stop it. They compact themselves down to these very small sizes, and then, as I will kind of explain better later, they become black holes. The other option is a neutron star. It's similar to a white dwarf in that it's just kind of this soup of subatomic particles, except in this case, it's neutrons. But with those, what's happened is the outside kind of recoiled off and got blown away. And now you've just got that like really dense core at the center. And in the process of recoiling, you produce things like higher level elements. So like uranium and stuff occurs naturally because a supernova occurred where we are now, and then we formed out of the remnants of that. But a neutron star and a white dwarf also can become black holes. And that's kind of what the next half of this will all be about. So the first way to being a black hole is just being a really, really big star. And so when you die, you collapse really, really fast and really, really hard and fall below what is called a Schwarzschild radius. So this is where it gets kind of heady and educational as opposed to fun. But we have to kind of cover these two important topics to understand what exactly is going on. So,
yeah. So what path is? How big is our sun compared to the other stars?
So sun would be on the average star path. So it's likely that it'll expand to be a red giant. I think the number is like it'll get out to about where Jupiter's orbit is, but on the order of millions, hundreds of millions of years.
Okay. And so then wait.
Yeah.
So do all the stars have planets like orbiting them?
We think a vast majority of stars have planets. It's actually kind of the other field that I studied, exoplanets. We have no reason to believe they don't, and from our observations, a lot of them do, but planets, because they're so small, are very hard for us to detect. So it's hard for us to know if they look we've only detected about 4,000 exoplanets. We think because they're hard to detect and not because there aren't that many.
Okay.
Yeah. So we think that it's likely most stars have 1 to 2 planets orbiting. They're very different from our own planets, but it's likely that they have them. Yeah, so are there any other questions here? I can answer a couple too if there's any waiting. I don't know if there was anything in chat I didn't see. Cool, I'll continue. So kind of the first thing we're going to talk about is Schwarzschild. He was an astrophysicist around the time of Einstein. And one thing that's important to everything happening next is that light acts kind of like a particle sometimes. So we like to think of it as not a particle as a wave, but it does kind of have mass and does kind of have a speed limit. But those are hard to pin down things because of how it behaves. We know the speed limit, we know the mass, but they're just kind of, they behave weirdly. But I think the easier way to understand this is kind of through analogy. So if I'm standing on Earth and I throw a ball directly upward, unless I threw it really, really hard, it would just come back down to Earth. If I threw it hard enough for the height that I'm throwing the ball from, I would be hitting the escape velocity. And at that point, the ball would leave Earth's orbit and just kind of go out into space and collide with whatever it ends up colliding with, or not collide with anything. If we were to imagine now, I could change the mass of the Earth without changing its radius. I could get the mass to a low enough point that the speed I can throw the ball would be the escape velocity. Alternatively, I could also change my radius to far enough away that the speed I throw the ball is also escape velocity. That's how it works. And I'll do a quick derivation following this to show what that means. But the biggest point is because light does have a mass and does have a speed, we can do the same thing. We just say the ball is the mass of a photon and the speed I'm throwing it is the speed of light. And now I can say what mass radius combination for planet and where I'm placed, or star and where I'm placed, is going to the speed of light escape velocity. So I think this derivation helps a little bit, but it is Dante's cool math corner. So be warned, this part is math. Kinetic energy is fairly commonly expressed as 1/2 mass of the object you're concerned with. In this case, our ball or our photon times its velocity squared. Gravitational potential energy is, you might not have seen it formed this way. You might have seen it formed a different way because you were just worried about on Earth, but generally speaking is expressed as the negative gravitational constant, which is just kind of a magic number that we calculated, times the mass of the bigger object, so in this case, Earth or a star, times the mass of the object that's moving, so whatever we're using kinetic energy for, so in this case, ball or photon, divided by your radius, which is the distance from the center of mass of the bigger object. If I'm interested in an object going at exactly escape velocity, that's just when the kinetic energy and the gravitational potential energy are equal. And so if I substitute in those equations I had, I can do some algebra magic that I'm not going to get into because that kind of would just be a waste of time, and say that, okay, well, I know then that the escape velocity of an object is the square root of 2 times the gravitational constant times the mass of the object I'm throwing it away from, divided by however far I'm away from that object's center of mass. If we take velocity to be speed of light, we can then say that Schwarzschild radius, which is what this equation is for, is 2 times the gravitational constant times the mass of the thing I'm on divided by c squared. If you notice, and this is kind of going to be the important thing to note here, as I make the object I'm throwing this ball away from more massive, the Schwarzschild radius gets bigger. So then kind of the next thing would be the chat. Okay, so yeah, the sun, to quickly answer that question, is in main sequence. So as I said, it's about halfway through its main sequence life. We think its life should last around 100 million years or so. So that would be where that falls. Oh, I gotta go back. Okay, so the next kind of thing is Pauli. I mentioned it earlier, and now I'll try to explain as best as I can without having a PhD in quantum physics what that means. It's basically this kind of weird quirk of quantum mechanics where we can't have 2 subatomic particles in the same state. And kind of the most direct and easiest way to think about this is just you can't have 2 subatomic particles, protons, neutrons, whatever, in the same physical location. There is more complication to that just because quantum physics kind of just says things can't be in locations. So there are some other things that go into it, but the easiest way to think of it now is just that we can't force 2 neutrons to be in the same place. This matters because when we're